Have you ever wondered what makes our modern electronics so incredibly fast, enabling instant responses and seamless operations? While devices often feel instantaneous, there is a fundamental truth in electrical engineering. Nothing happens truly instantly, especially when it comes to the tiny components that power everything. Transistor switching speeds are not instantaneous primarily because of inherent physical properties within the device itself, including parasitic capacitances, the need to store and remove charge carriers, and the internal resistances that limit current flow. Let's dive deeper into why this is the case. First, every transistor, whether a field effect transistor or a bipolar junction transistor, possesses parasitic capacitances. These include capacitance between the gate and source, and the gate and drain. When you try to switch a transistor on or off, these capacitances must be charged or discharged, which takes a finite amount of time determined by the resistance and capacitance, often called an RC time constant. Second, in bipolar junction transistors, switching involves the storage and removal of minority charge carriers in the base region. To turn the transistor off, these stored charges must be swept out or recombined, which is not an immediate process and adds to the delay. Finally, internal resistances within the transistor and its connections also limit how quickly these capacitances can charge and discharge, further contributing to the switching delay. For engineers, understanding these limitations is crucial for designing high-speed circuits. You can mitigate these effects by selecting transistors with lower parasitic capacitances, which typically means smaller physical dimensions. Additionally, employing stronger gate driver circuits helps to charge and discharge these capacitances more rapidly, speeding up the switching process. However, these improvements often come with trade-offs, such as increased power consumption or manufacturing complexity. These delays are quantified by specific metrics like transition time and propagation delay. Transition time refers to the time it takes for the output to change from one state to another, typically measured from 10% to 90% of the final value. Propagation delay is the time required for a signal to pass through the transistor from input to output. The RC time constant, a product of resistance and capacitance, is a fundamental concept that directly governs these delays. Recognizing these specific terms allows you to precisely analyze and predict circuit behavior in high-frequency applications. Ultimately, the non-instantaneous switching of transistors is a direct consequence of fundamental physics and material properties. These inherent delays define the operational limits of all electronic devices and circuits, from microprocessors to communication systems. By understanding and carefully managing these factors, engineers continuously push the boundaries of performance, achieving ever faster and more efficient electronic systems, even though true instantaneous action remains an engineering ideal.